Electric fields and potentials. We're going to talk about electric field lines and how we can visualize them and some important key points about electric fields. So an electric field is actually experienced around a lot of charges, and it extends through space, basically an infinite distance depending on the strength of the charge. If you have a positive charge, the field lines would go away from the positive charge, whereas if it's a negative charge, the field lines would be pointing towards the charge. So it goes out from the positive into the negative. And we're going to have a little activity and some questions regarding this. So you're going to want to make sure that you understand the field lines go out from the positive and into the negative. Now, these field lines are equally spaced apart, and that's really important that you understand they're equally spaced apart. So the field lines point away from the positive and towards the negative. Now, these field lines represent lines of force. They indicate the direction that the force would be acting on the point charge or on the charges. This way, if a charge were to leave the surface or if a charge were to move, it would move along those field lines. Now, field lines go out from the positive and towards the negative. So we would always draw it out from the positive and into the negative. So opposites attract, we'd move it from the positive charge to the negative charge. And that would be the direction of the charge motion. Now, it's also really important that we understand that since field lines are lines of force, the closer together those lines are, the stronger that force is going to be. So therefore, the stronger the field is going to be. Also, the more field lines there are, the stronger that force is going to be as well. So more field lines, the stronger the field. So the closer the lines are together, the stronger. The more field lines are, the stronger. And they go out from the positive and into the negative. And these are really key points in understanding and answering questions you're going to be asked about field lines. Here we have some pictures, and I really want to focus on the top two pictures. The one on the left shows two oppositely charged charges. One's positive and one's negative. Notice the field lines are going out from the positive and into the negative. Because you see field lines between the positive and negative, you'll note that that means that they're attracting one another. Now, the one on the right has two equally charged positive charges. And notice the field lines are going out from the positive charges, and these blue lines are the field lines. They're going out from the positive charges, and there's a space between them. And what this indicates is that the two are repelling. So how would this be different if they were both negative? Well, if they were both negative, the blue lines would look identical except for one small change. Do you know what that change would be? Instead of the field lines, the arrows going away, the arrows would point towards if they were both negative. So if they're both negative, the arrows would be opposite. So out from the positive, and the arrows go towards if they were negative. So what is electric shielding, you might ask? Well, if you've ever had something struck by lightning, it's actually safer to be in a metal container like a car if you're struck by if a vehicle is going to be struck by lightning or if there's a lightning storm. You would not want to actually stand underneath the tree because lightning would travel through the tree to the ground and the electricity would pass up through you underneath the tree. So it's actually safer to be in your car. Now, the electricity is going to move along the metal frame of the car, and that's going to protect you in the center because there's no electric field in the center. So as long as you're actually not touching the frame of the car or anything metal, you're actually safe in the center. And this is actually true for airplanes. I'm not saying that it's actually the best idea to fly in a thunderstorm. However, if a plane is struck by lightning, the electricity moves along the frame, along the metal, which keeps us protected or shielded on the inside of the airplane. In fact, the biggest reason why airplanes get grounded during these thunderstorms is actually the wind shear. It's the wind shear that actually is the biggest issue. So if you have to take cover, it's best to do it in something that's metal where you're protected, because electricity would move along the metal frame. So then what is electric potential? Okay, what is an electric potential? An electric potential actually has to do with the force and the energy supplied based on the charge's location. So if you have a charge and you want to move it from one location to another location, and you have two positive charges, they want to repel one another. And so that requires work to be done to move the charge. To move that charge, work has to be done. Now, since work is energy and energy is work, in this case, that work to move that charge requires electric potential energy. Potential energy because it's moving location or position. Electrical because we're talking about electric charges. So the work or the energy required for that charge to move. Now, in order for that to happen, we call this electric potential difference. Electric potential difference is the amount of work or energy supplied to the charge to move the charge from one location to another. The more common term that you may have heard for this is called voltage. Voltage is the electric potential difference. So it takes a difference in energy supplied to a charge to make it move around or move from one location to another location. Now, a charge actually has a quantity, a numerical value. And if we're talking about a proton or electron, the specific numerical quantity or magnitude of that charge is 1.6 times 10 to the negative 19 coulombs of charge. And so the amount of energy supplied to that charge is the amount of potential difference or electric potential difference, also known as voltage. The voltage or the electrical source, like an outlet or a battery, it is actually like a pump. It actually provides the energy to the charges to cause it to move from one place to another. Now, we also have a device called a capacitor that you might find in a lot of electrical devices. And a capacitor actually stores up electrical energy, so it can act like a temporary storage of energy. So it's like a temporary battery. Now, a lot of these are really, really tiny because we can actually find these in our cell phones and tablets. And so they're not really big, but there's also really big ones for larger devices. Okay, so they range in size and in shape, actually. But what does it do for us? Well, you may note that with years have passed, if you had an early cell phone, it took a lot longer for the cell phone to actually start up. And so what they do is they have these capacitors that actually store up a little bit of the energy. And this way, it actually can provide some of that energy to the charges to go ahead and get the circuit started without having to wait for the battery or the electrical outlet to kick in. And so that actually gives it a head start to actually go ahead and get your device working. Once your device is turned on, it will then actually recharge itself so that it's ready for the next time it's needed. So how do we know this information about electric field? How can we visualize an electric field, and how do we know that they actually exist? Well, in some cases, you can feel the electric field. There's a machine called a Van de Graaff generator where you can actually feel the static electricity. And you've probably felt static electricity by scuffing your feet along the floor and touching a doorknob and having the electricity shoot out from your finger, or you've probably shocked somebody around you before and felt that electricity. And so these kind of things actually happen, and we feel the electric field around us in a regular basis. But how could we visualize that? This is actually included here so that you have a chance to actually see some electric fields and kind of get an idea of what that might look like.
Parts about teaching the electric field is that it's invisible. You can't see it, but you can investigate it with various apparatus. In this video, I will teach you 10 activities and experiments that you can use to help make the electric field a little bit more visible. The plasma globe itself already looks like an electric field. Specifically, it's the electric field of a spherical charge in a grounded conductor. That's just the inside, but on the outside of the globe is where the real action is. You can see the electric field invisibly extends far beyond the glass when you use it to illuminate fluorescent bulbs. It truly is the strong electric field that's doing this. You see, the high electric field pulls the electrons off their nuclei in opposite directions, ionizing the gas. The electric field is radially pointed outward, which you can verify by taking a small linear tube and rotating it. It shuts off. It only works when you can establish a high voltage between the two ends. And that is one way to calculate the electric field, a difference of voltage over distance. You'll also notice that the electric field is not strong when you're far from the globe. You can see this with a neon or a diode. Nope, it gets weaker with distance. You can also verify this with an oscilloscope probe. The y-axis on an oscilloscope is a voltage reading, and this reveals that the electric field of the plasma globe is changing at all times. You can verify that the voltage is decreasing as 1 over R as measured from the center of the globe. Be sure to have the ground input as far away from the plasma globe as possible, otherwise it may interfere with the measurement you're making. Now, you can use the change in voltage over change in distance formula and make direct measurements on an electric field. But be careful, because your body can act as an antenna and will interfere with the results. One more thing. You can demonstrate that there is no electric field drop in a conductor. Once the bulb starts glowing, it becomes a plasma, which is a conductor, and as you pull it out, you get more and more of the conductor. This might help you discuss electric fields and circuits. The Van de Graaff generator is a must-have when teaching electrostatics and the electric field. For example, you can use it to show that the electric field is higher near pointy edges than rounder ones. You see, it is the electric field that ionizes the air and makes lightning. A pointy edge can do that easier because the electric field is higher. Notice also that these lightning rods are connected to the ground. Of course, you can also use the Van de Graaff generator to demonstrate radial electric field lines. For example, you can tape streamers on the top of the Van de Graaff and they will point radially outward. Or you can use a human. Find a long-haired human and have her stand on a milk crate for insulation. Remove all metals such as rings and glasses and zippers, and with any luck and dry weather, her hair will stand up. Another way to demonstrate electric fields with the Van de Graaff is to hang a string over the charged dome like you're going fishing. Watch as the charged string is amusingly repelled by the electric force field. But I think the most convincing way to show the electric field is with a straw cut in half and pinned to a meter stick. Now you can probe the space around the dome effectively. If you want to demonstrate the electric field of two like charges, get a second dome but do not connect it to ground. Their electric field lines will point away from each other, just like two positively charged electric fields. Take a petri dish and fill it with some cooking oil or mineral oil, and then stick 2 electrodes in it like these 2. Then mix in some seeds. I like to use lettuce seeds, though many people use grass seeds. Then if you charge up the wires, you will see motion of the lettuce seeds. They will move to align themselves in the electric field. This apparatus is available for purchase from vendors, but you can make it yourself with coat hangers if you follow the instructions in the description below. It's important that the electrodes be well insulated. hence these plastic stands. By the way, my source of charge has been this fun fly stick for the positive side, and I use my finger for the negative or ground side. I used to use a Van de Graaff generator, but I find this to be much more convenient. Anyways, with this setup, you can show various features of the electric field, such that it's perpendicular to conductors, and that there is no electric field inside of a conductor. See? The seeds aren't moving. It might be helpful to use a gooseneck camera or overhead projector to project the demo on the big screen so that everybody can see it and appreciate it. It's actually possible to map a real electric field using carbon paper with electrodes on its surface. What you're actually doing is mapping the voltage difference between 2 points and then graphing the voltage lines throughout. And if you can accept that electric field lines are perpendicular to voltage lines, then you can graph a real electric field in 2D. The hard part is figuring out what to use for the electrodes. You can use conductive silver ink, or, if you can get it, metallic tape. Some people even use actual bars of metal, but the silver ink seems to work the best. A reasonable voltage to set is between 12 and 20 volts. This won't shock you, but the measurements will be easy enough because the numbers are large. The result is that you get these nice voltage maps. And since the electric field is perpendicular to the equal potential lines, you can map the electric field near these conductors. Experiment and get creative with your electric fields. A real problem with this lab is that it takes a long time. You want to work to ensure a streamlined data collecting procedure, and you probably want to draw in the electrodes for your students on the graph. But the results are usually very good.
And that's our information about electric fields and potentials.